The ideal gas law. So what's the big deal? Well, if you can predict really well what the pressure or volume or pressure of a gas is going to be, it makes our life so much easier and safer, right? Whether it be pneumatics or some molecular structures that are turning into gas valves. But maybe the easiest application is right here and very useful. You're a potato chip manufacturer and you fill your potato chip bags with air or some gas, right? Well, sooner or later, these potato chip bags are going to end up in a really hot room. So as the temperature increases, the gas molecule speed increases, pressure increases, those bags are going to expand. And you just don't want those bags to pop, right? So that's a good application of the ideal gas law. Have you ever thought about this? Why airplanes fly? Gas pressure has everything to do with why airplanes can fly. If we have a wing, what's its shape? Well, it's flat on the bottom and curved up on top. Now we know that there's atmospheric pressure everywhere. So if you want this wing to go up, to have some lift, the pressure above the wing has to be low. Has to be lowered somehow. The pressure has to be lowered because you have atmospheric pressure on the bottom. Right? You have atmospheric pressure down here. So the pressure above the wing has to be lower, and then the wing will go up. Well, how is that generated? Well, the wing's traveling through the air, right? And the air has two choices. It can travel below the wing, or it can travel above the wing. If it travels, well, here's the wing distance from here to here. So if it travels below the wing, it has to go from here to here, right? A straight shot. But if the air travels above the wing, it has to travel from here, go around this curved surface, and end up over there, right? So it has farther to travel. But yet it has to reach the end of the wing at the same time as the air below the wing. So the air on top of the wing is traveling faster. You have fast-moving air above the wing. And fast-moving air simply cannot generate as much pressure. Fast-moving air reduces the pressure. So that is how pressure is lowered. In fact, this whole thing is called Bernoulli's principle. That's why airplane wings allow airplanes to fly. They generate lift. So I can demonstrate Bernoulli's principle with this card with a toothpick in it and this rubber stopper that has a hole in it. What I'm going to do is put the rubber stopper over on top of the card like that. I'm going to blow as hard as I can through this hole. Now what's going to happen? As I blow through as hard as I can through this hole, the air is going to come out on the bottom of the stopper and just come out on across the top of this paper. And remember, fast-moving air exerts less pressure. So there's going to be less pressure on top of this card than there is below it. So if there's less pressure on top, I'm going to generate lift. Let's try it. So when I stopped blowing, the pressure was the same on both sides, and the weight of the card made it fall. Bernoulli's principle. Cool. The ideal gas law equation. Well, what is the equation? It's just PV equals nRT. And what are the units for each variable? Well, go by R. R is the gas constant, and that's what determines the units for everything. The R that we're going to use is 0.0821 liters times atmospheres over moles times Kelvin. So that kind of tells you what the units are for every variable. P has to be atmospheres then. V would have to be in liters. N would be in moles. We already know what R is. And T always has to be in Kelvin. So go by R, and you'll know what the units are for all the variables. Our ideal gas law equation, but with molecular weight in the equation. What is the equation? PM equals dRT, dirt. How about the units for each variable? Well, R we know. It's the same. P. Let's start with P. P should be in atmospheres then. And we know what R is. T has to be in Kelvin. Now this is supposed to be an equation with molecular weight, and that's this. There's our molar mass. And remember what the units are for molar mass? Grams per mole. So the only thing left is D. D is density, the density of the gas. And if you take a look at all these units, for this to work out, density has to be in grams per liter. And then your units will be fine. According to your calculations, a reaction should yield 5.67 grams of oxygen. What do you expect the volume to be at 23 degrees Celsius and 0.985 atmospheres? Okay, here's all of the equations we have so far. Which equation applies? The trick to doing this, I think, is that you would see multiple pressures and temperatures and volumes if you're going to use that expression. But that's not in here. We don't have multiple pressures, temperatures, or volumes. So that means we're either going to use this expression or this one. Well, they didn't tell us the density of the gas, so I'm not worried about that, although we could use that equation and it would work. The most straightforward equation to use is PV equals nRT. So my pressure is 0.985 atmospheres. They want to know what the volume is. N is 5.67 grams. Now that's the wrong units, but recognize mass, units of mass, right? So I have 32 grams in a mole of oxygen. 5.67 divided by 32, about 0.177 moles of oxygen. R, 0.0821 liter atmosphere per mole Kelvin. T is 23 degrees Celsius. But we have to add 273 to that, so it's really 296 Kelvin. So now we can substitute everything in. PV equals nRT. P is 0.985 atmospheres. V equals N, 0.177 moles. R, 0.0821 liter atmosphere per mole Kelvin. And T is 296 Kelvin. So we just solve for V, and your units have to come out in liters. So 0.177 times 0.0821 times 296 divided by 0.985, about 4.37. Butane is an easily liquefied gaseous fuel. Calculate the density of butane gas at 0.897 atmospheres and 23 degrees Celsius. Give the answer in grams per liter. Great, because that's what's going to come out in. They're asking for density, so it's pretty obvious what equation to use. PM equals dRT. So we just need to know what all those variables are. Pressure is 0.897 atmospheres. M has to be the molar mass in grams per mole. I have 4 times carbon plus 10 times hydrogen. You get about 58.14 grams per mole. Density is what I'm trying to find. And we know what our R is. The T is 296 Kelvin again. So if I substitute into my expression, I'll get 0.897 times 58.14 has to equal D times 0.0821 times 296. So what's my density? And it will come out in grams per liter. 0.897 times 58.14 divided by 0.0821 divided by 296, around 2.15 grams per liter would be the density of butane. A 1.28 gram sample of a colorless liquid was vaporized in a 250 ml flask at 121 Celsius and 786 millimeters of mercury. What's the molecular weight of the substance? We don't have a whole lot of choice. We're going to have to use PM equals dirt. So my pressure is 786 millimeters of mercury. Wrong units though. Let's divide it by 760 to get it into atmospheres. 786 divided by 760, about 1.03 atmospheres. M is what we're trying to find. How about D? D is grams per liter, right? So just divide the grams by the liters, and you'll have grams over liters. Here's the grams. Here's the liters. 1.28 grams divided by 0.25 liters. We'll have the density. 1.28 divided by 0.25, about 5.12 grams per liter. And I need to know my T. My T is 121 degrees Celsius. Add 273, you get about 394 Kelvin. That's how I'm good to go. PM equals dirt. Pressure is 1.03. Solving for molar mass. Density is 5.12. R is 0.0821. And T is 394 Kelvin. When I solve for molar mass, I get grams per mole. It's 5.12 times 0.0821 times 394 divided by 1.03, about 161 grams per mole. So try this one. See if you can get the same answer as me. A 2.5 liter flask was used to collect 5.65 grams of sample. After the sample was collected, the gas pressure was found to be 741. What was the temperature of propane in the flask? We've got a couple choices here. We could use PV equals nRT to find temperature because we know the pressure, we know the volume. We can find the number of moles because they told us the grams and they told us what the compound is, and solve for temperature. You could also use PM equals dirt if you want, but I'm just going to use PV equals nRT. So my pressure is 741 millimeters of mercury. I need to divide that by 760. 0.975. My volume is 2.5 liters. Those units are good. My N, number of moles, is 5.65 grams. Let's convert that into moles. I've got 3 times carbon, 12.01 times 3 plus 1.01 times 8, a molar mass of around 44.11. About 0.128 moles. So I'm ready to substitute into PV equals nRT and solve for T. Pressure, 0.975 atmospheres. Volume, 2.5 liters. Moles, 0.128. Our gas constant, 0.0821. And solve for T. And T will come out in Kelvin. 0.975 times 2.5 divided by 0.128 divided by 0.0821, 232 Kelvin would be the temperature of the gas. So here's your big test. See if you can solve this one and get the same answer as me. They're looking for molecular mass, so I'm just going to use PM equals dirt. So I have to know everything but molar mass. My pressure is 985 millimeters of mercury. So I'll get that into atmospheres. (985) divided by 760, about 1.29, about 1.3 atmospheres. Molar mass is what I'm looking for. Density, that's in grams over liters, so 2.30 grams all over 0.345 liters. 2.3 divided by 0.345, about 6.67 grams per liter. T is 148 Celsius. At 273, you get about 421 Kelvin. So if I substitute all this in, I have 1.3 atmospheres times molar mass. My density is 6.67. Gas constant, and temperature 421. My sulfur molar mass, it'll come out in grams per mole. 6.67 times 0.0821 times 421 divided by 1.3, 177 grams per mole. So working out these problems I don't think are too bad. Just watch your units and remember that have everything determined by the units of whatever the gas constant are, and that density is always in grams per liter. If you remember that, I think you're going to be good. Good luck.